we are talking about, just to begin with, let's activate the poll once again, and I have just a couple of questions for you, which I believe would set the trend, would set the agenda. Okay, so the first poll coming to you is all right. Can you see that poll? Can you see that question on your screen now? What is the maximum remainder when you divide any number by 401? I hope you can see that poll, and there are 5 options there: 1, 399, 400, 401, and can be infinite. So I can see some people answering one by one. Let's see what is the correct answer. It says, the question again, what is the maximum remainder when you divide any number, it could be any big number, small number, whatever, by 401. When you divide something by 401, what is the maximum remainder that you will ever get? All right, so that's quite interesting. I'll just give you probably 5 more seconds to respond. Okay, so I can see that almost 87% have voted already. Let me all right, so let me just give you the results. I think a couple of people are still waiting, but I'll just tell you what exactly were the answers here. The question again was what is the maximum remainder when you divide any number by 401, and none of you responded to the first option 1. 23% responded to 399. 31% responded to 400, 31% responded to 401, and 15% said it can be infinite. Well, that's interesting. Okay, so we'll come back to this question, but and we'll see how this can be done properly. So let me close that poll and let's see how to solve that. Okay. All right, you can see the poll results on your screen now. I hope you can see that. The same results, 88% have voted. There are still some people who have not voted. But the maximum number of votes, as they do in KBC, are 400 for 400 and 401. It's 29% each. So obviously, there is a very close answering situation here. There are quite a few people who think that it's 400 or 401. So somebody who is on the KBC hot seat can probably not take his decision based on this, right? So let's see what is the correct answer. Okay. I'm closing the poll. I hope you can see my screen now. And let me just check. Yeah, you can see my screen now. So let me write down a couple of things here. Okay. All right. So we said, what is the maximum remainder when you divide a number by 401? So if you divide something by 401, what is it that you would get in the end? This box. Now, division is a fairly simple thing, and I'm sure a lot of people have done remainders. You've been teaching remainders as well. Division in particular. So if I were to divide something by 4, let's say I divide 17 by 4. Okay. So 4 times 4 is 16, and I get 1 as the remainder. If I increase the 17 to 18, okay, so if I make this 18, my answer would have been 2. If I had made this 19, my remainder would have been 3. If I had made this 20, my remainder would have been 0, because then this would have been 4 times 5, and that's 20 here. So obviously, the maximum remainder that I would have got is 3. Okay, so it's quite obvious. Although I intentionally put this huge number here, 401, just to see whether you understand the concept. So this remainder effectively cannot be more than the number itself. So the maximum remainder that you can ever get is 400. All right. Which is, quite a few people had 400 and 401 were the most popular choices, and 400 seems to be the correct one. All right, so let's move on. Let's move on to the next one, and this is, what is the minimum remainder when you divide a number by 401? What is the minimum remainder when you divide a number by 401? This seems to be a tricky question. So there are a lot of people have responded to 0, a lot of people have responded to 1. Nobody is going for 400 or 401. So I'm going to give you 10 more seconds. Okay. 5, 4, 3, 2, 1, and 0. Okay. So we can't really wait endlessly. So let me just share the results. All right, so what you see here is 47% say 0, 47% say 1, and 6% say 401. And we were talking about the minimum remainder. Okay, so we were talking about a situation, what is the minimum remainder when you divide a number by 401? Now this is a slightly tricky situation, and we can come back to this later as well. But I hope some of you have heard of negative remainders as well. Right? So if there was ever a negative remainder, then obviously the answer would have been none of the above, which unfortunately nobody has marked here. Technically speaking, 0 is the correct answer, because you can't go below 0. But there are situations when remainders are negative as well. Okay, so we'll come back to this. Thanks so much. All right, so I'm going to hide this and move on to the next one. Okay, here goes. The next question, if a number is divisible by 2 as well as 3, as well as by 3, it must be divisible by, and you can actually have multiple correct answers here. It's not only one of them, you could have a lot of them. Okay, so the choices are 6, 10, 12, 20, and 24. All right, again, kind of a trick question. And I'll give you, let's see, 10 more seconds starting now. Quick. If a number is divisible by 2 as well as 3, it must be divisible by, take all the correct ones. All right, time up. Let's close this and show you the results. The results. So 100% people have voted for 6, and there are 50% who have voted for 12, 39% who have voted for 24. 86% people voted, so 14% are still remaining. Anyways, so the issue is this correct? Is this hypothesis correct? If a number is divisible by 2 as well as 3, it must be divisible by 6 obviously is the correct answer, but is it the only correct answer, or will it also include 12, 24? Nobody has taken 10 and 20 for obvious reasons. But let's consider a couple of examples. So 2 times 3 is 6, so that's why most of you have made it 6. Now suppose I say I take a number 18. Is 18 divisible by 2 as well as 3? 18 is divisible by 2, 18 is divisible by 3. But is it divisible by 12 or 24? No. So obviously, if you're talking about all the, it has to be divisible by 12 as well as 24, it becomes an incorrect answer. All right, so let's move on. Okay, now this is the next one. Again, a slightly tricky one, but this is exactly the reverse. It says if a number is divisible by 12, it must be divisible by 2, 3, 6, 8, and 24. 2, 3, and 6. Very good. Okay. A lot of you have voted in favor of 2, 3, and 6. 10 seconds to go. 5, 4, 3, 2, 1. And closed. All right, so let me just share this result here. I think most of you have got it right. 2, 3, and 6 are obvious answers. There are just 5% people who have voted for 8 as well, which seems to be incorrect because if you have a number which is 12 itself, I mean, consider 12 itself because 12 is divisible by 12. Is it divisible by 8? No. Similarly, 24, of course, except 12, there are other numbers as well. For instance, 12 times 3 is 36, but that is not divisible by 24. Okay, so we'll come back to this idea. How does it work and everything? But it just goes to show that we should be very comfortable with our basics in mathematics before we face a class of hostile learners. All right, so there's just one last quiz that we will attempt, and then we'll move on. Okay, last quiz question. Can you get a negative quotient in division? Okay, I think I gave out the answer already, but let's see. No, yes, no, yes. All right. Can you get a negative quotient in division? And we're talking about quotient. Quotient is we had talked about remainders, and I said that remainders could be negative. But can the quotient be negative? Can the quotient be negative? That's very interesting. 5 seconds to go. 4, 3, 2, 1, and closed. All right. Now, this is interesting. 57% say yes. 43% say no. Quotient cannot be negative. But 57% say yes, it can be negative. Now let's see. Let's consider an example. These are quite tricky questions because negative quotient happens when you consider negative numbers to be divided or to divide, right? So let me go back to the screen now, and let's understand if there are any. Okay, let me see if you can actually see my screen now. Not. I hope you can see my screen. Let me see if you're able to see it. I think you're still able to see only the poll result. So let me just erase this and then start again. Okay, so I think we are back on the same screen now, and we can, let me erase all of this, and let's go back to the question of whether there could be a negative quotient. Now, what is a quotient, first of all? So if I divide if I divide 7 by 3, I hope you can see what I'm drawing here. 3 times 2 is 6 and the remainder is 1, and this number here 2 is called the quotient. Can this be negative? Now that was the question. A lot of you have said yes, and a very small number, equally large number actually, has said that it could be. Oops. Quite a few people have actually said that it could be negative as well. So let me see how can it be negative? Okay. Suppose I have 3 and minus 22. So minus 22 divided by 3. So obviously you're going to get a negative quotient here, and that would be. Now this is again an interesting question, because whether it would be 3 times negative 7 or will it be 3 times. So let's see how it works. So 3 times negative 7 is negative 21, and then so this must be positive. So 21 minus 22, so that is minus 1. So that is one answer. Then the other way of doing the same question is 3 times minus 22. So instead of minus 21, I should come up and say that 3 times minus 8 is minus 24. And when I find out the remainder, it becomes 24 minus 22, that is 2. So in one case, I'm getting a positive remainder. In another case, I'm getting a negative remainder. So obviously, there are several ways of doing this. We will see how or which one is correct. In fact, I think it's a good research area to figure out which one could be correct. All right. Okay, so let's move on. All right, what we are going to deal with is common rules of divisibility. I hope you can all see the screen. Let me just expand it. Okay, common rules of divisibility. What we are going to do is I have clubbed them together in 5 different groups. 2, 4, 8. I'm sure most of you would know what are the rules. So I'm not going to spend a lot of time on the rules themselves, but how did we arrive at them is more important. So the group 1 has 2, 4, and 8. 2, of course, you know the divisibility rule is the last digit has to be even, or more generally, I mean, generally speaking, last digit has to be divisible by 2. Similarly, for 4, the last 2 digits have to be divisible by 4. So it could be 0, 4, 0, 8, 12, 16, and so on. In case of 8, if you're checking divisibility by 8, the last 3 digits have to be divisible by 8, and that also includes the triple zeros. Okay, so there could be 3 zeros or 2 zeros or 1 zero, of course. So divisibility rule by 8 includes a situation when you have 3 zeros, okay, in the end. Now, sum of digits must be divisible by 3 or 9 in case of 3 and 9, if you're checking by 3 or 9. We'll go to these individual stuff later on when I'm trying to explain the reason behind it. Group 3 has 6, which we've already seen, divisible by 2 and 3. Now the interesting part is whether the same rule applies to 12, 24, 48, and so on. Okay. Group 4, there are 2 parts to it. One is 11 and the other one is 7 and 13. 11, of course, most of us know is when you try to find out the difference of sum of the alternate digits. Sounds a little complicated, sounds a little tongue-in-cheek kind of things, but you know, we can try it out and then it'll become clearer. The group 4B is 7 or 13. Now both of them are slightly they are not really discussed a lot, but there is a one popular rule which is basically you make alternate groups of 3 starting from the right hand side, the units place, and then add these alternate groups, and then just like in case of 11, You add all these groups together and then find out the difference of the two sums. Again, it might sound a little complicated at this point of time, but we can discuss this later. The fifth one is chain rules. These are actually different, entirely different set of rules that apply to divisibility. Okay, and finally, we will also see modular arithmetic, which is quite complicated, quite an advanced topic, but how to simplify your problems using modular arithmetic. We'll not go into deep things into modular, but we'll try to find out how to apply modular arithmetic in our divisibility area. Okay, so let's move on. Okay, so basics. I just wanted to cover a few basics here. What are the basics? I mean, basics meaning there are a couple of concepts that you should know, and we will try to cover some of them very quickly. Expanded notation, I'm sure quite a few of you know this already, but here it goes. So 24,938. Okay, so this I'm sure you all know. We can write it in an expanded notation. So let me begin with the units place. So I can write 8 times 10, sorry, 8 times 1. Okay, so I should have deleted it, but let's move on. 8 times 1 and 3 times 10, and you would have 9 times 100, and you would have 4 times 1000. So this is how you write the expanded form. This is very handy when it comes to finding out the reason behind how divisibility rules work. Okay, so that's why you have to be a bit patient. So that is the expanded notation. I'm going to refer to it again. So I thought it's important to write it down. All right, so that is one. The other important concept, the basic concept, is remainder properties. Okay, and I'm saying remainders flow through addition or multiplication. Let me explain what I mean by that. Now, remainders flow through addition and multiplication. It simply means that if you have, say, 7, if you divide it by 2, you get a remainder of 1. And if you have, let's say, 11 and you divide it by 2, you again get a remainder 1. Now, the interesting part is the remainders will also follow through or flow through the addition and multiplication operations on these two numbers, 7 and 11. Okay, so if I add both of them, 7 plus 11, okay, that's 18. Now 18 divided by 2 gives you a remainder of 0, right? And if I add these two remainders, 1 and 1, obviously 1 plus 1 is 2, and 2 divided by 2 will also give you 0. So you can actually add two numbers and the remainders will also get added up. Similarly, the multiplication will also hold true. So 7 times 11 is 77, and we all know that 77 divided by 2 will give you a remainder of 1, and 1 times 1, that's the product of the remainders. So 1 times 1 is also 1, right? So 77 divided by 2 will also give you a remainder of 1, and the product of remainders is also 1. This is a very, very basic concept, but it's very useful when it comes to analyzing or trying to understand the way things go. Okay, so let's move on. Now the other important stuff is cyclicity in powers. Okay, cyclicity in powers is a very, very powerful concept when it comes to divisibility rules. Now let me just quickly do what I've indicated here is this is 10 power 1. Oops, sorry. Okay, so this is 10 power 1, this is 10 power 2. So what I've written is these are the powers. 1, 2, 3, and so on till 8. So there are 10 powers 8, so that you don't end up counting number of zeros. So I've written these powers here, and let me talk about the remainder when you divide something by, let's say, 3. So if I divide 10 by 3, I get a remainder of 1. If I divide 100 by 3, I get a remainder of, again, 1. Okay, because 3 times 33 is 99. Okay. Now, if I divide 1000 by 3, again 999, right? 999 is a multiple of 3. So I get a 1. And it goes on like this. So all of these powers will give me 1. Similarly, even 9, if I were to check with 9, it'll again give me the same remainders, 1, 1, 1, 1 in each case. And I'll come back to this when we are trying to explore why the divisibility rule for 3 or 9 holds true. Okay, so we'll come back to this again. Let's move on. In fact, let's do one more example here. So let's talk about remainder when divided by which number should I take? 7. Okay. So 10 divided by 7 will leave you a remainder of 3. 100 divided by 7 would leave you a remainder. Now, this is interesting because some of us may not be very conversant with multiplication tables. In fact, I would hate to remember all of them. But 7 times what goes into 100. So even if I don't remember, it doesn't matter because 100 is actually 10 times 10. And we know that remainders flow through multiplication as well. Okay, so 10 would give you a remainder of 3 that we already know. And this 10 will also give you a remainder of 3 that also we know. So 3 times 3 is 9. And 9 divided by 7 is going to give you a remainder of 2. So that's an easier way of doing this. Of course, if you know 98 goes, 7 goes into 98 perfectly. So 98 is actually a factor, multiple of 7. All right, similarly, 1000 is, now it becomes easier because 1000 is 100 times 10. So you just need to multiply 3 and 2 together and you would get the remainder for 100. So which is 3 times 2, that is 6. Similarly, 10,000 is 1000 multiplied by 10. Or you could do 100 multiplied by 100, either ways. So 100 multiplied by 100 is 10,000. So obviously this must be 2 multiplied by 2. The remainder must be 2 multiplied by 2, that is 4, and so on. So the next one could be this 4 multiplied by this 3. So 4 times 3, that is 12. And 12 divided by 7 gives you 5. The next one, I wanted to go on because there's something interesting here, which will actually derive the rule for 7. So 5, when it comes to power of 6, so 5 multiplied by 3, right? So 5 multiplied by 3, that is 15, and 15 divided by 7 gives you a remainder of 1. Now this is the most critical aspect here. Whenever you get a remainder of 1 in such situation, you should know that after this it's going to be repeating. That's why I call this a cyclicity in powers. So the next one obviously is going to be 1 times 3 because 1 was from the power 6 and 3 was from 10. So 1 times 3, that is 3. And then of course it has to repeat because 3 times 3, that is 9, and 9 divided by 7 is 2. Okay. So you can see that there is a pattern here. The pattern, let me write in a different color so you get to understand this. And the pattern is you get 3, 2, 6, 4, 5, and then 1. And then it again repeats 3, 2, 6, 4, 5, 1, and so on. Now this is something interesting. This is what will actually determine the divisibility rule. And one more interesting part is the 6 number, which is actually 7 minus 1. And we'll hold on to this thought before coming back to this. Okay, so let's just move on. Now group 2, 4, and 8. 2, 4, and 8, and we said that if a number is divisible by 2, the last digit has to be, if one number is divisible by 2, the last digit has to be 0 or 2 or 4 or 6 or 8. In other words, the last digit has to be divisible by 2. Similarly, for the last two digits have to be divisible by 4. So it could be 0, 0, 0, 4, 0, 8, and so on. Okay. And it's a long list, so I'm not going to write this down here. Similarly, for 8, it is 0, 0, 0 or 0, 0, 8. So these are the last three digits, right? Sorry, 8, 16, and so on. Okay, so this is how the divisibility rule goes. And why does it happen? I think that's the first question that comes to my mind when I see this pattern here. So why does it happen? It happens because, let me erase all of this and then we'll start again. So let me write down some number here. Let's say 4, 9, 5, 6. Okay, 4956, and I want to check whether this is divisible by 4. We know that it has to be doing with the last two digits. Why last two digits? Because if I write this in partially expanded form, I can write this as 49 times 100 plus 56. I can write this like this. And 100 is divisible by 4. Okay, so the remainder from this 100 is going to be 0. Anything multiplied by 0 multiplied with 0 is 0. So this entire thing cancels out. The only thing that is left out is 56. So that is why they say that the last two digits have to be divisible by 4 or they have to be zeros. Because this is the only thing that matters, you know. The rest of it, even if I keep adding some random numbers here, it doesn't really matter. Okay, so all of this number will be divisible by 4 if 56 is divisible by 4. And we all know that 56 is divisible by 4, right? Similarly, now this is where this concept comes in. When we were talking about the remainders when divided by 7, let's go back, erase all of this, and let's see if this also holds true. Remainder when divided by 4, 10 divided by 4 is the remainder of 4. Sorry. 2. 100 divided by 4, remainder 0. And 1000 divided by 4, again going to be 0 and so on. Okay. So the interesting part is, as long as we know that 100, any multiple of 100, it will give you remainder of 0, I think it will hold good. All right, so coming back to this, similarly for 8, the last three digits, because why last three digits is because 1000 is divisible by 8. Okay, so this remainder will give you 0. This remainder is 0. So obviously now I'm sure you can imagine what would be the rule for 16, because 16 is nothing but, if I were to divide 10,000 by 16, it's quite predictable that the remainder has to be 0. Now what is so special about these numbers? Speciality is 2 raised to power 1 is 2, 2 raised to power 2 is 4, 2 raised to power 3 is 8, and 2 raised to power 4 is 16. Now 2 raised to power 4 is 16, and we are talking about 4 zeros here. So the general rule is the number of zeros will determine the number of digits that you need to follow for 2, 4, 8, 16, and you can continue like this, right? So you can make it 32, 64, 128, and so on. Okay. All right. So let's go back to one more poll. I'm fond of these quizzes, you know, and so that you also know that you're understanding it every time I ask you something. So let me activate one more poll, one more question. So I'm sure you can see that question here. The question is, what is the highest power of 2 that will divide some huge number? I'm sure you know what that is, right? It's a huge number. What is the highest power of 2 that will divide 9, 8, 7, 6, and so on? Okay. All right, 5% have voted. I'm just waiting for everyone else here. All right. I'm waiting for the others to key in their answers. 53% have voted, 58%. Okay, last 10 seconds. Last 10 seconds. 5, 4, 3, 2, 1, and 0. Okay. So let me share the poll results with you. You can see that almost everyone has voted for 5, which is 2 power 5. And just like I said, you just need to count the number of zeros at the end, and that's your answer, right? So 5 is the correct one. Let me just count that number again. Yes, there were 5 zeros, and 2 power 5 is 32. So that's the maximum power that will go into it. Okay. All right. So let's move back. Let's move back to the next slide. Running short of time, maybe we'll continue in the next session. So 3 and 9, group 2, 3 and 9. Let's try and do 3 and 9. I don't want to rush into this because there are things here which you would want to know, and especially when you're trying to teach your children about divisibility, it's important that they know what is the logic behind it. Now 3 and 9. Okay, let's go back to the cyclicity table, and we said that if there was let me erase all this. Okay, if we made this 3, then the remainders were all 1s, right? Similarly, if we replace this with 9, again the remainders were all 1s. Okay, so with that with that knowledge, let's go back to understanding why this 3 and 9 works. So let's write down a number here. Let's say 6, 4, 3, 9, 8, 7. It's a long number. The rule says that you add the alternate digits, okay, and then find out the difference. Now, why does that happen? Okay, why? Because we know that, again, writing in the expanded form, I could write this as 7 into 1, 8 into 10, 8 times 10, 9 times 100, 3 times 1000, 4 times 10,000, and 6 times 100,000. Okay. Now, we all know that all of these are meaningless when it comes to remainders, because all powers of 10 are going to give you a remainder of 1 if you divide by either 3 or 9, right? So 1 divided by 3 will give you a remainder of 1, or even by 9. Similarly, 10 divided by 3 or 9 will give you a remainder of 1. 100 divided by 3 or 9 will give you a remainder of 1, and so on. So all of these are going to give you a remainder of 1 only, right? So obviously, when everything is going to give you a remainder of 1, we don't need this huge calculation here. So what we can simply do is, I just need to multiply everything by 1, okay, and then add all of them together. Now, why add? Because it was a part of the expanded notation. We said 7 into 1 plus 8 into 10 plus 9 into 100 and so on. So what remains as the remainder is only the sum of these digits, and that's the way the rule goes, right? So if the number is, the sum of the digits is divisible by 3, the number is divisible by 3. Similarly for 9. Okay, that's fairly simple. Let's move on to the next one, which is 6. Now this 6 is an interesting one, because it also tells us whether we can apply the same stuff to 12, 24, 18, and so on. Okay. Now 6 has 2 prime factors, 2 and 3. Okay. So very naturally, we know that if a number is divisible by 2, it has to be, if I want to find out rule for 6, I need 2 different numbers which go into 6 perfectly. So 2 times 3 is 6. So obviously any number that is divisible by 2 as well as 3 will go into 6 perfectly. Okay, that's kind of dirty. Yeah, let me write this again. So 6 is 2 times 3. So any number that goes that is divisible by 2 as well as 3, that as well as 2 and 3 is very critical. Okay. Now that is fairly simple. Now let's go to 12. Okay. So shouldn't because 12 also has two prime factors, 2 and 3. Okay. So that should also hold true. But we saw that there are numbers like 18, which is actually a multiple of 2 as well as 3. But this is not a multiple of 12, right? So obviously there's something wrong. The problem is that we have 12 written as 2 square times 3. It's not 2 times 3, it's 2 into 2, that is 4 times 3. So what you need to do is, you need to check for 4 and 3, not 2 and 3. Now it will all hold true, because when you're talking about, let's say 24 is divisible by 4 as well as 3. So it must be divisible by 12 and so on. Okay. So that's a very critical point here, and I'm sure you should give your class some more exercises on this, because this question has to be very clear. Okay. All right. There have been some questions on my pane. Somebody has asked about what about division with 4, 5, and so on. Okay. I think we've discussed 4, but let's. I thought it's not important to discuss 5 because everybody knows the last two digits. Last digit has to be 5 or 0. Similarly, 10 last digit has to be 0 and so on. Let's move on. 11. Now that's the interesting part, and this I think is the beginning of the session where you begin to understand what is happening. Okay. So let's again take some number here. I think I'll have to take a big number, crazy number. Okay, that's enough. And again, expanding the notation. So it's 2 times 1, 6 times 10, 8 times 100, 4 times 1000, 5 times 10,000, there's 100,000, and of course 8 is 1,000,000. I hope I've put in all the zeros correctly. But anyways, so let's find out what is the remainder when we divide these powers of 10 by 11. Okay, so when I divide 1 by 11, obviously the remainder has to be 1. When I divide 10 by 11, the remainder is 10. 100 by 11, the remainder is again 1, because 11 times 9 is 99. For 1000, I really don't need to do that. I know that 1000 is 100 times 10, so I can take these two numbers and multiply. So I should get 10. For 10,000, I can do, 100 square of 100, so 1 times 1, that is 1 again. So I'm sure you can see that pattern. Okay. Now, what is interesting is that I can actually write this 10 as 11 minus 1. All of it here, 11 minus 1, 11 minus 1. And that's why this rule works, because we are talking about the alternate places. Let me use a different color here so you can understand this better. So I'm talking about, let me circle all the digits that left us a remainder of 1. Okay, so 2, 8, 5, and this one 8 again. And the other digits left us a remainder of 10, which we converted into 11 minus 1. Now, obviously, when I'm talking about 11 minus 1 here, let me use a different color again. So if I have a 11 minus 1 here, and I were to multiply 7 times 11 minus 1, so I would get 7 times 11 minus 7 times 1, right? Now this 7 times 11 is obviously a multiple of 11, so I don't need to worry about this because this is going to give you a remainder of 0. What you're left with is minus 7 times 1. Okay, Similarly, this one is going to give you minus 4 times 1. And this 6 is going to give you minus 6 times 1. So effectively, we have reduced this entire big equation, big expression here into two parts. One is 8582, that is divisible by that you need to multiply by 1, and the remaining is 746, which is multiplied by negative 1. And now I'm sure you can see what is happening here is, finally, if I were to write this in a summary form, what I would have to do is 8 plus 5 plus 8 plus 2, and I could write this as plus 7 plus 4 plus 6, but this has to be multiplied by minus 1, right? So obviously, effectively the rule is the sum of alternate digits. We're talking about sum of alternate digits, 8 plus 5 plus 8 plus 2, and since this is a minus 1 here, so I can make this minus 7 plus 4 plus 6 in the other bracket. So effectively, this is how the rule for 11 works. And this, I should tell you, is the crux of the session. If you understand 11, now everything will become clear. Okay. I can see some raised hands here. Let me see if anyone wants to say something, because we are going to be ending the session in a short while. I don't want to exceed the limit of 1 hour. But let's move on. Let's see. Guneet, if you have something to speak up, should I pass on the speaking rights to you? Let me see. You've raised your hand for quite some time. Guneet Kaur, I'm passing on the speaking rights to you. Is there anything that I can help you with, Guneet? I'm sorry.
No, my doubt is clear.
Okay. Thank you. All right. So, okay, let's move on quickly. 7 and 13. Now this is actually a takeoff from 11, where we left 11. This is where 7 and 13 would begin. Okay. Now, instead of writing down the entire sequence here, let me go back to this huge table here, and let me see if I can erase this. Okay, it doesn't seem to be working. But let's see if I can show you 7 and 11 here. Okay, so 7 and 13, let's write it down here. Okay, the remainders when you divide something by 7 or 13. 7 we have already seen, so let's work with 13 now this time. So 1 divided by 13, sorry, 10 divided by 13 is going to give you a remainder of 10. We can quickly do this. 100 divided by 13, I don't need to do, although I know 13 goes into 91. So 100 minus 91 is 9. Now the next one obviously is a multiplication of these two. 10 times 9, that is 90. And 91 goes into 13, so obviously the remainder has to be 12 here. Now this is again the interesting part, where we said that 12 can be written as, 12 can be written as 13 minus 1, right? And then we move on. 12, the next remainder would be 12 times 10, that is 120, okay, and so on. So you can keep working on this, and you would find that the 6th power is going to give you that magical number 1. Okay, so the 3rd power gives you 12, and 6th power gives you 1. Okay, in case of 11, what had happened was, in case of 11, this had given you 10, and 2nd power had given you 1. Okay, and we had written 10 as 11 minus 1. So that kept alternating, right? So we had 10, 1, 10, 1, and so on. Now I hope you're getting to what I'm trying to deliver here. we are talking about the third power giving you a remainder of 13 minus 1 and the sixth power giving you a remainder of 1. Okay, so let's quickly go back to 7 and 13 screen here, and the same holds true for 7 if you remember. Okay, so let's quickly write down again some huge number. So let's write down 6, 7, 4, 3, 9, 8, 6, 5. Let me add one more. I don't know why this got erased here. But anyways. Okay. Oops. I need to write again. 2, 9, 8, 7, 5. Any random numbers. You can actually write down your own as well while we are doing this, because it could be quite boring to look at a screen writing on itself. So you could do something of your own. Okay, here we go. So we know that the third power. So this is multiplied by 10, multiplied by 1, and then 9 multiplied by 10, 6 multiplied by 100, 7 multiplied by 1000, right? And what was remainder? Remainder was, let's talk about 7 initially, and I'm sure you'll figure out 13 as well. So 7, 1 divided by 7 will give you a remainder of 1. 10 divided by 7 gives you a remainder of 3. 100 divided by 7 will give you a remainder of 3 times 3, that is 9. 9 divided by 7 gives you a remainder of 2. Okay, I hope you're getting what I'm trying to do here. And of course, there should be a plus sign everywhere. So 1000 is 100 times 10. So I can actually multiply these two powers to get a 6. So 1000 is going to give me a remainder of 6, which now I can easily relate to as 7 minus 1. Okay. Now 8 oops, there's something tricky here. Let me use this option here. Okay, I'm sorry. I think we'll have to bear with the technology here. 3, 4, 9, 7, 6, 5, 3, 2, 8, 7, 8, 6, 8, 5. Okay. Now we said that this third power, 10 power 3, is going to give you a remainder of 6, which I can write as 7 minus 1. Okay. And we also know that there is a third power. This will be the fourth power. This will be the fifth power, and this will be the sixth power, right? And we also said that 10 power 6, we saw that 10 power 6 is going to give you a remainder of 1. You can work this out yourself as well. So now I can clearly see that I can group this in 7 times 10 power 3. Now this will give me 3 times 10 power 6. You can also see that I can write this as plus 685. I can actually write this as 287 times 10 power 3. And similarly, I can group these three and write this as 653 times 10 power 6. And then again these three as 497, because this is going to give me a remainder of 1, and so on. 10 power 9. 12. This was 10 power 9. Okay. Now I know that all of these, 10 power 3 is going to give me a remainder of minus 1. Right? And this one is going to give me a remainder of 1. So I can quickly alternate these. So this one is going to give me a remainder of 1. this power 9 is going to give me a remainder of -1. This one is going to give me a remainder of 1. So I can now club them together in groups of 3. So I can have 685 plus 653 plus 3. Now these are going to give me a remainder of +1. And then I need to subtract this because there is a -1 remainder somewhere. So I need to subtract 497 plus 287. This I'm going to subtract, right? So this is what determines the rule for 7 and 13. Okay. Now the interesting part is both of them work here. Both 7 and 13 work here. Although it's not a very, it's not really an easy solution to work with. You need to add a lot of numbers, but everything. But still, it's easier than dividing something and finding out, right? So let's just. I think we've already crossed the time limit, but let me see if there are any questions here. Divisibility for 18 is not clear. Let's just wind up after taking a couple of questions here, okay? So divisibility for 18 is not clear. I think somebody has asked about divisibility of 18. So let me just go back to 6. Okay. So here we were at 6, and let's see how to get divisibility of 18 in the picture. Okay. Now divisibility of 6 we all know is 2 times 3. So let's also write down for 18. 18. How do you factorize 18? 18 is 2 times 3. 2 times 3 is 6, and 6 times 3 is 18. Right? So obviously, I need to figure out with 2 and 9. Okay. So if I were to figure out whether a number is divisible by 18, I need to take into account 9 and 3. Remember, you need to take the highest power of the prime factors that you come across. Now this is fairly simple because if you have any number and you're trying to check for 18, first of all, you need to check whether the number is even or odd. So if the number is odd, it can't really be a multiple of 18. And then once you confirm that it's even, then you can figure out whether the sum of the digits is equal to 9 or not. Okay. So this is how it will progress. Let me just quickly move on to, I think if you can quickly do an alternative. There are some interesting things that would happen here. So I hope you can bear with me for a few more minutes, because this is where things become more interesting. Okay. So 21. Would you know anything about 21? Rules of 21. Now let me give you the rules, and then I think I'll leave it to you, to your imagination, to work out whether how will this work out. Okay. Now 21. I can see that 21, I can reduce 21 to 0. Oops. Sorry. I can reduce 21 to 0 if I do 1 times -2. Okay. Or let me put this in raw words. If I were to take the last digit, multiply it by 2, double it, and then subtract it from the remainder, subtract it from the other part, this will work. So let's look at some larger numbers. 684. Okay. Now how do I check whether this is divisible by 21 or not? What I do is I take this, I split this into 2 parts. 684, I make 68 separate and 4 separate. I multiply this by 2. Okay, so I get 8. And then I subtract 8 from 68, so I get 60. And I don't need to go ahead because I know 60 is not divisible by 21. Okay. Now this is something that will also work for 7. Very interesting. The same rule will also work for 7. And till now I'm sure you've understood why these rules work and so on. So I think you need to explore it yourself. Why does this work? I mean, why does it work? And one of the just to kind of clue is if you had any number of the form 10a, 20a plus b, okay, and you can work with this logic here and try to figure out, again going back to the expanded form and so on, then you're probably able to figure out what is happening. Okay, so let me just erase off this, go back to 13. Now 13 is an interesting number again. Now one more way of finding out 13 is, how do I make this 13 by doing something with the last digit? Okay, now obviously if I'm looking at 3, can I multiply this by 4? So I get a 12, and then I add it to the remaining one, that is 1. Okay, so basically what I'm trying to say is, the rule is multiply the units place, multiply the ones place or the units place, ones place, ones digit by 4, and add to the remaining number. Now that's interesting. Again, I am not going into the details of how you figure it out and so on. I'm sure if you go back to all the previous basics, I'm sure you'll understand this. So let's take some number which we know is a multiple of 16, which is 13, which is 169, which happens to be a square of 13. Okay, so let's apply this rule. 9 times 4, so I get 9 times 4 is 36, and 16 plus 36. I need to figure this out quickly. So that's 52. Okay, I know 52 is a multiple, but let's keep continuing. Assuming let's assume that we don't know. So 2 times 4, that is 8, and 5 plus 8 is 13. Now, of course, we know that 13 is a multiple of 13, right? So this is how 13 will work out. Let me erase this again and go to 31 now. Now, as we did with 21, now it's quite intuitive. Just like we doubled the units place in 21, now we need to triple the units place in 31 in case of 31. So let's see. If I have 9, 8, 4, 3, and I want to find out whether this is divisible by 31 or not, what I do is first I take the units place multiplied by 3, so I get 9, and then subtract from 984, so I get 975, right? And then again I split this into 97 and 5, multiply this 5 by 3, I get a 15. So this is what I meant by the chain rule, because you have a chain forming here, right? So you get 82. Then again I could, if I don't know, 831 table, I can go ahead 2 times 3 and you get 6. So 8 minus 6 is 2. Obviously it is not divisible. So unless you get a 0 or a multiple of 31, you can keep doing that, okay? I think you would have figured out 41 yourself. I don't need to worry about that. But the next one, 23, is quite interesting. Now, 23, I need to figure out how to come to 23 by doing something with the units place. You might ask me why I insist on doing something with the units place. Why not tens place? Because when we are trying to do a chain rule, you don't want to end up in an even larger place, in even larger number than the original number, because then it becomes a very impractical solution. So here what we're trying to figure out is, what number can I multiply this 3 with and add it to 2 so that I get 23 again, okay? So I know 23 minus 2 is 21. So if I multiply this 3 by 7, I get a 21. And then this 21 I add back to 2. That's when I get 23 again. Now this seems to be a pretty tedious solution. So let's not take a large number. Let's take a 432. Okay. And again, what do I need to do? I need to multiply the units place by 7. So units place is 2. I multiply it by 7. I get 14. And I need to add them. Okay. So I get 7 here, 5 here. I still don't know whether this is divisible. So let's again multiply this by. Actually, you end up getting a bigger number here. So you might as well would have tried 57. Okay, so 54. So obviously, neither 54 nor 57 are divisible by 23. So we'll forget about that. Okay. All right. So 23 works well. So you could actually try it yourself on different other numbers. One tricky area is you would have noticed that I've taken prime numbers here. You would also want to know what happens if they are composite numbers here, right? But we'll leave that to your working later on. Let me just end the session with a stupendous number here. So let's talk about divisibility by 13. I know it's considered as an unlucky number, but I'm fond of this number, divisibility by 13, and we have a huge number here. Now, modular arithmetic, applying modular arithmetic. Let me not go into the details of modular arithmetic, but let me just say that what we've discussed till now also sums up as if there is a number that gives you a remainder of, let's say, 2 by dividing it with some number 7, then I can actually replace that original number by 2 by the remainder, So that's the crux of what modular arithmetic means. Okay. Let me just quickly try and apply it to the task at hand. All right. What it simply means is if you have such a huge number and the rule of 13, either one of them, we discussed 2 of them, both of them would make it very, very difficult to work with groups of 3, adding them together, subtracting them, and so on, right? It would become very, very difficult. Okay, so let's not worry about that right now, although I'm marking it for some reason. Now, what I want you to do is, I want to figure out which are those sets of numbers here, 2 digits or 3 digits, that you remember in your tables of 13, okay, which are either close to these numbers or are multiples of these, okay. So I know that 13 times 2 is 26. Do I see 26 here somewhere? Yes, I see 26 here. So let me use a different color so that it becomes clearer. So I see 26 here. Basically, modular arithmetic says that you can actually replace this 26 by the remainder, which is 0. Okay, but that sounds very crazy. But why does it work is because, again, going back to the expanded notation, this is actually 26 multiplied by, how many zeros I need to add, 5 of them, right? So basically, what it means is 26 times so many. 26 times 100,000 is somewhere in the expanded notation. Okay. Now I know that 26 is a multiple of 13, right? So if 26 is going to give me a remainder of 0, then the entire thing is going to give me a remainder of 0, and that is why I replace this 26 with 0 and 0. Okay. Now similarly, can I locate something which is closer to 26, a little larger? I mean, maybe 27, 28, 29 here. Very nice. So I can make this as 0, 3, okay? Because 29 divided by 13 is going to give me a remainder of 3. All right, let's look at any other numbers. I can see that there is a 78 here, which is, again, I know is a multiple of 13. I see 79 here, which is multiple plus 1, okay? Is there anything else that I see? 79 again, so I can see 0, 1 here, okay, and so on. So let's just write down this whole number again using all these replacements, okay, and let's see how it simplifies our problem. So 985, instead of 79, I have a 0, 1, then I have a 0, 0, 698. Now 98 also is pretty close, so I'm trying to get as many zeros as possible. So 98 will give me a remainder of oh, I didn't replace 98 here. Let's leave it as it is. Let's not worry about that. Okay, and then 79 as 0, 1. Then I get a 0, 8, 4. I can actually replace other stuff as well. So let's talk about 84. Okay, I know that 13 goes into 78. So 78 plus 6 is 84. So I can make it 0, 6. I can replace this with 0, 6. And then I have in fact, 52 also would have gone into 12. 52 is also multiple of 13, but Let's not worry about it right now because we already replaced the zeros here. So 5, 0, 0, then you have 0, 3, and then let's leave the remaining as it is, okay, instead of worrying about it. Now you can see there are a lot of zeros now here. Why did we have so many zeros here? Because when we were trying to add these groups of 3 here, there were a lot of digits. Instead of that, now I have zeros, okay, so that's how it helps. Now you can again replace stuff. 13 times 5 is 65, so I can make this 0. That helps a lot. 69 would give me a remainder of 0, 4. Now the only important point to note here is that you need to replace these with 0, 4, not 4. Otherwise, this entire thing will go wrong. Okay. I know that 91 is a multiple, so I can replace this with 0, 7 as well. Okay, so let me keep the remaining as it is, and so on. Okay, so 8, 0, 1, 0, 0, 0, 0, 0. 3, 8, 4, 3. Do we recognize anything here? 13 times 3 is 39, so 43 can be made as 0, 4. Now 38 is a tricky thing. Of course, just to bring home that point, 38 is actually 39 minus 1. So I can actually replace this as minus 1. But we can't write minus 1 in a number. But we can replace minus 1 with 13 minus 1, that is 12. Okay. This is an important substitution here. Although it may not help a lot, but this is how it appears. So now you can see that there are a lot of things that have been simplified, and you can again make a group of 3 and keep on doing that. So this is where I would end it. I don't want to bore you with so much of calculation here. I think it's better that you try it out after this point, and you can figure out whether this is divisible by 13 or not. Now the important point is divisibility and remainders go hand in hand. So if you are finding out divisibility by 13 and you find out that it's not divisible by 13 and it ultimately gives you a balance of 4, then it is actually giving you a remainder as well. It's not just about divisibility. It's also giving you one step ahead, and it's actually giving you remainder. Okay. All right. I saw one note here from someone, and let me just find out who said this. We can think of 69. 69 in this. Yeah, of course. I think I just did that. So let me just close this. All right. So this is where I would end the session. I know that we've gone a little ahead of the scheduled time, but let's close this here. Thank you so much for being here. I would handle any questions if you have any questions here. Okay, I see that there is one more question that I had for you. Just to end everything with one more question. You can see that there is a question on your screen which says, will the divisibility rule for 81 be the same as that for 3 and 9? We saw that 3 and 9, is it just a coincidence that 9 is the square of 3? And then 3 times 3 power 3 would be 27, 3 power 4 would be 81. Just like 2, 4, 8, 16, 32, 64, and so on, would 81 follow the pattern? Now 44% have voted. I'll just wait for 10 more seconds for you to vote, and then we can. I'm assuming that anybody who doesn't vote is actually going in for the third option, which says can't say, right? Okay, time up. So let me share the results. 54% are saying yes, 38% are saying no, and 8% are saying can't say. And there's still 9% who have not really voted, so I can add 9 and 8. That is 17% are saying can't say. All right. So I think you need to ponder over that question. It's an interesting question because again, it helps you to build those concepts with your students very quickly. Will the divisibility rule for 81 be the same as that for 3 and 9? I think it should be no, but you can check it yourself. All right. That's about the end of it. Let me just also share with you that This discussion was brought to you by Beyond Teaching, which is basically the fastest growing teacher network in India. And we keep on trying to do a lot of stuff for teachers. You can probably keep frequenting the site. One more important thing is that we have a few more webinars coming up. We are keeping Fridays as the webinars because I thought that it would be easier to keep Fridays because the next day you don't have a hectic schedule to follow. I'm hoping that Saturdays are either non-working or you may have a less tedious schedule. Okay. So the next webinar is planned for Google in your classroom. How to use Google in your classroom. I'm sure most of you use Google all the time, but how do you use Google effectively for your classroom? The March 8th seminar is teaching, again, discussion on Vedic math for speedy calculations. I don't know if a lot of people are very enthusiastic about speedier calculations nowadays because of calculators and computers in our lives. But still, I think simply because competitive examinations don't really allow calculators, computers in the hall, you need to calculate faster. And then we will be following it up with 2 consecutive sessions of CTET, which is a Central Teachers Eligibility Test. Unfortunately, in the last test that happened in November, less than 1% of people actually qualified CTET. So just as a concern towards the teaching community, I think we would do 2 sessions on CTET math. And these are the upcoming sessions. You can keep looking at the beyondteaching.com website for more webinars. Thank you so much. If you have any questions or anything to talk about, please raise your hand and I'll pass on the speaking rights to you. Thank you so much again. Thanks for your time.